So at this point, we've talked about the power rule, we've talked about some trig antiderivatives. We're just going to throw in a few other indefinite integral formulas. So the antiderivative of e to the x, we did this one earlier actually, it's just e to the x plus c. And again, just check your answer if you're unsure. Take the derivative of e to the x plus c, derivative of e to the x, that is e to the x. C is a constant, so derivative of that term is 0. If we have the integral of dx over x, or the integral of 1 over x dx, or I might even add one more case if I have both of those are the same as saying x to the minus 1 dx, that is natural log of absolute value of x. So here we do need to be a little bit more careful. We need to put this absolute value around x just to make sure that we reflect the domain of the function that we began with. So we're beginning with 1 over x, which has a domain of all real numbers except for 0. If you look at natural log without the absolute value, if you were just to say natural log of x, we can't take the natural log of a negative number. So we want to kind of expand our domain to account for that. So the way we do that is we say, okay, we're just going to put these absolute value bars around x so that it makes that result positive. That means I can take the absolute value of that number. So it is something that I'll be looking for. It's not a huge deal, but it is something that we should be including in our answers. Natural log of absolute value of x. And then the other three that I would throw in there as well are the inverse trig derivatives that we learned. So if I want the antiderivative of 1 over square root 1 minus x squared dx, that is sine inverse of x plus c. If I have the antiderivative of dx over 1 plus x squared, that is tangent inverse of x plus c. And if I have the antiderivative of dx divided by x times square root of x squared minus 1, that is secant inverse of x plus c. And again here, we're just kind of generating these from the derivative rules that we already know. So I know that the derivative of sine inverse of x is 1 over square root 1 minus x squared. I know that the derivative of tangent inverse is 1 over 1 plus x squared. It's been a while since we've looked at these, but we're just kind of repurposing the knowledge that we already know. And we're going to practice using these other indefinite integral formulas. We'll look at a couple of tricks here. First I have is integral e to the x over 3 dx. So this one I actually think is surprisingly tricky. We say, okay, I see that e to the x. I'm thinking about this indefinite integral. I know that the indefinite integral of e to the x is e to the x. But what do I do about this 3? What do I do with that? Do I need some sort of quotient rule maybe? Or, well, it turns out it's simpler than that. E to the x divided by 3. If we divide by 3, that's the same as multiplying by 1/3. So 1/3 times e to the x dx. And then I know, hey, 1/3, that's just a constant multiple. So I can factor that out. 1/3 times the antiderivative of e to the x dx. And now I've simplified this down to exactly what my antiderivative formula for e to the x says. It says if you want to find the antiderivative of that, it's just going to be e to the x plus c. We just need to make sure that we include this 1/3 with our answer. So 1/3 times e to the x plus c. We also could have written this as e to the x over 3 plus c. So please keep an eye out for multiplication and division. As long as it's by a constant, usually it's not going to present that big of a deal. But if I wanted to integrate, say, e to the x, if I wanted to integrate, say, e to the x divided by x dx, that is actually going to be a lot more complicated when we're dividing by, say, a function of x. If it's just a constant, we can factor that out. But remember, we can't factor out a function of x. So this is right now a problem that we don't really understand how to do, and maybe we'll learn by the end of class, or by the end of this class. Next up, I have part B. I have 4 over 3 times square root 1 minus x squared minus 3 over x dx. I look at this, I see that square root of 1 minus x squared in the denominator. I say, hey, this looks like, this guy right here looks like the derivative of sine inverse of x. I also see 3 over x, and I say, hey, that looks an awful lot like 1 over x. First thing I'm going to do, though, is I'm just going to simplify this. I'm going to break it up into a few different integrals just because this does look a little bit more complicated than the types of functions we've been working with. So I'm going to first of all say, well, this is the integral of 4 over 3 radical 1 minus x squared dx minus integral 3 over x dx. I'm just going to make two separate integrals. And then I'm going to say, okay, are there any constant multiples that I can factor out that'll make this a little bit easier to look at? In this first integral here, I really have 4/3. That is actually just a constant multiple. I can factor that out. So I can say that's really 4/3 times the indefinite integral of 1 over square root 1 minus x squared dx. And this, I think, is a lot more easier to manage because, hey, that looks exactly like the derivative of sine inverse of x. 3 over x, this 3 right here, I can really just think about that as 3 over 1. So I can factor out that 3 once again, just like I did with the 4/3, and that will leave me with 1 over x dx. And this is nice. It's a little bit easier to work with because now these two functions that I'm trying to integrate, that I'm trying to find the antiderivative of, look exactly like our examples up here. We know that the antiderivative of that first term, that's going to be sine inverse of x. The antiderivative of that second term, that's going to be natural log of absolute value of x. So I should have 4/3 times sine inverse of x minus 3 times natural log of absolute value of x, plus again my constant of integration c. Yes, we still need that here. So this is my antiderivative, my indefinite integral. Oops. One more example that we'll look at here. This one's a little bit different. Here I have the antiderivative of 4x cubed plus 2x divided by 3x squared. And this actually looks like an example that I just kind of threw out there earlier. I said, hey, if we had, say, e to the x over x dx, right now we don't have the tools for that because we don't really have a quotient rule. We can't really deal with this. This is it's a function in the denominator, so I can't just factor that out. So just like with this function here, I can't just factor out this 3x squared because of the x squared part. I could factor out the 3, but you'd still have that function in the denominator that's causing you a problem. There's still really not a great way to get rid of that. So we need to be creative about our solutions and think back to, we actually dealt with problems like this when we did derivatives. If you have more than one term in your numerator, so in this case I have 4x cubed, and I have 2x, I can just split this up into two separate fractions. I can say, well, that's 4x cubed divided by 3x squared, and 2x divided by 3x squared. So I'm going to break this up into two separate problems. I'm going to say, well, this is 4x to the third divided by 3x squared plus 2x divided by 3x squared. If you want to break it up into two separate integrals, that's fine. Usually I don't bother. I just kind of do it without even thinking. And at this point, I can say, okay, we can simplify each of these two terms. I can say, well, 4x cubed over 3x squared, that's really 4x divided by 3, plus over here, this is 2 over 3x dx. And now, okay, this is perhaps a little bit more complicated. Now we have an x in the numerator, an x in the denominator. I want to make sure that I'm not making any silly mistakes. So I'm going to, first of all, split this up into two separate integrals. The integral of 4x over 3 dx plus the integral of 2 over 3x dx. And then I say I want to simplify this even further, so let's take care of those constant multiples. I'm going to factor out the 4/3, I'm going to factor out the 2/3. So 4/3 times the integral x dx plus 2/3 times the integral of 1 over x dx. You probably could have jumped straight from this second step right here down to this step if you're comfortable with the algebra, but I'm just trying to show all of my steps here in these first few examples. So 4/3 times the antiderivative of x dx here, this is just going to be a regular old power rule, the very first rule that we talked about. So 4/3 times, I should really have x squared after I add 1 to the power, divide by my new power of 2, plus over here 2/3 times the antiderivative of 1 over x dx. We said that is, 1 over x, that's the derivative of natural log. So the antiderivative of 1 over x, that is natural log absolute value of x, plus, of course, my constant of integration c. And this term right here I can simplify, otherwise it's just going to bother me. So I can write this as 2/3 times x squared plus 2/3 natural log absolute value of x plus my constant of integration c. You could factor that and clean it up and simplify it if you really wanted to, but I would say I think that that's probably a good place to stop for this problem. I wouldn't go any further here.